Right. In this course in dynamics, which we are doing, we are going to study about vibrations. Okay. Now, what's vibration? What is vibration? Like waves. Okay. Okay. Any other example of vibration? Sorry? Spring. Okay. If you disturb a spring, it vibrates. Very nice. So many things vibrate. If you take a bell and you sound it, it vibrates. So you perceive it because your eardrums are vibrating. My vocal cords are vibrating, exciting a lot of stuff. In fact, that speaker over there is vibrating, right? And physics says that every body is vibrating because of only at absolute zero there's going to be rest. But we don't feel many of the vibrations because the mean or the overall vibration of all the particles cancel out some of the others. So we don't feel a lot of stuff vibrating. They feel at rest. And is vibration good? Good? Okay. So this is a very tricky question to ask because we have the earth vibrate a little as what happened in Bhuj. Yeah? Yes, buildings collapsed. So now that makes vibrations a little difficult to understand. There are good vibrations, there are bad vibrations basically. See, if you look at your heartbeat, periodic. So suppose that vibration or that constant motion is not there, something is very bad, something very dangerous is happening. And in fact, you can capture that on your ECG machine or something, and then you see that some there's something changing with reference to time in a periodic manner. When it's not periodic, you are worried. So heartbeat, again, you are peddling the cycle. So that is something I think you have seen. So things like this, everywhere vibration is happening. So what is the thing that you're going to say vibration is? Vibration is when something is moving about what we call as a mean position, we say that vibration is happening. Strictly speaking, maybe there are cases where it doesn't move exactly about a fixed point. But then you'll find that in all the cases of vibration, you are going to be in a position to say that there is a mean point and we are moving up and down above it. Okay? So you'll find that it can be a displacement, it can be a velocity change, it can be a change in acceleration, and it may not be the linear acceleration, it can be a circular oscillation. For example, if you look at a clock's spring, you see that the gear wheel is rotating between left to right. So that's one sort. Then there are also torsional vibrations. Okay, you can have a vibration in a torsion because something is twisting about its own axis. So quite a lot of stuff is happening when we use the word vibration. There is a book by a gentleman, Bishop, R.E.D. Bishop. He starts this way: you can't even say vibration without the tip of your tongue vibrating, right? So vibration is everywhere. And so is finally vibration good or bad? Very difficult to say. Medically, if you look at it, there are many equipments which massage or which cause a vibration to do a variety of things. Sports injuries treated, facials, they give some massage with the some device, and you are supposed to feel good, and body pain is removed. Now, once if you go to your washing machine, at least I saw it in my washing machine, the vibration makes the whole thing shudder. Okay, it's probably making the parts loose. It's probably making the it's increasing the wear and tear than when it would have been simply rotating. So again, there's one more point probably at this point which you can bring out. You have noticed that your cell phone vibrates. How does your cell phone vibrate? There's this very small motor, very small motor, and they keep an eccentric mass about. There's a disc, and on the disc there's an eccentric mass. So when that disc rotates, it starts to feel. You start to feel a vibration. Okay, so that's the principle with which any of the devices where vibration is felt, vibration response is there, is typically doing it. Of course, there are some piezoelectric sensors which can do it, but typically you will find that there's a motor involved in most of the vibrating devices which you get. Again, look at it. The mass is oscillating about a mean position. Okay. Now, just have a look at what this vibration is doing. On the speaker, we are keeping a non-Newtonian fluid and see what happens to it. So basically, the viscosity change is what we are looking at. It's not starting. Seems to be some problem with my videos. Okay, video is not playing. Basically, what happens is this is a solution made with cornstarch, when which is nothing but a powder, much like your atta or something. You put it in and then you oscillate it at a constant frequency. You will find that the viscosity increases. You find that the viscosity increases, and so sometimes vibration can do some very funny things at 30 hertz. 30 hertz means 30 times the speaker is oscillating about the mean position in a given second. Now there are two kinds of vibrations, the free vibration and the forced vibration. What is free vibration? When you are taking an object which can move about its mean position, and then you give that a displacement or a change in the position, this displacement, or you change its velocity, or you change its acceleration. Do any of this. See, initially it's at rest. I am changing the state of rest. So there's a rate of change of velocity. There's a change in first position. There's also change in the rate of change of displacement is there. Okay, and you can keep looking at it. So rate of change of velocity is acceleration. And when you do that, and you allow the body to try to come back to its original position, then it's called free vibration. Okay. So the vibration which will just be which will be continuing without the external agency continuing to give a forcing function, we call it as free vibration. Now, what is a forcing function? Suppose you have a device which is going to oscillate, okay, and you are continuously giving the force, then we call it as a forced vibration. Suppose you are sitting on a swing. This is something which you can easily relate to, and somebody pulls you. Initially you are at rest, you are the equilibrium position, so there is a displacement. Somebody is disturbing you and releasing you. What happens? The swing keeps oscillating about its mean position till it loses all its energy content. Essentially what's happening, you will immediately say there is a potential energy which is increased to kinetic energy, which again is shifted to potential energy, and this process repeats in an endless cycle. But there is a villain in the picture. Something is preventing this oscillation to continue indefinitely, right? So maybe suppose I am looking at it. What is this which is stopping the child from enjoying the swing? What stops the child? Sorry? If I am going to pull the swing and release it, the child is supposed to be, the total energy, potential energy is again converted to kinetic energy to potential. This has to be going on infinitely, but it is not happening, right? What is stopping? Which force? Yeah? Is the pulling force stopping the child? I have pulled the child, released the swing, I am moving back. Okay, so the child is freely oscillating. So this is free vibration. Now, my question to you is, what happens? Does the child continue to do this infinitely? Will he keep doing this continuously? No, you are right. So what happens to the child? It stops. But does it stop immediately? No. Okay. Why is it not stopping immediately? Because the energy change keeps happening. But what happens? Why is the child stopping? Sorry? No? No. Is it no movements? Are you sure? Okay. Then what could stop the child? Think you are sitting on the swing. What do you need to do to be? Yeah, there's no force, so that's free vibration. So, strictly speaking, something is making you lose energy. What is making you lose energy? Have you ever bicycled? Is it easy to cycle with the wind to your back or with the wind blowing against you? Huh? You move in the direction of the wind? If you move in the direction of the wind, is it more comfortable? Okay. Now in the swing, look at the thing which happens. The child is having what we call as a bluff area where the wind can hit. So does the wind help the child or does it make the child slow down? Slow down. Again, if you see the hinges of the swing, there are two kinds of swings where you pull the child and it's squeak, squeak. Another one is nicely oiled. Now, where will the child stop faster? Okay, wind is there. Now I am telling you about the hinge. Okay, there's a hinge at the end of the swing. So one hinge is making a squeaking noise, and the child is sitting on that swing. The next swing you have put a lot of oil, nice ball bearing is there, and there's no noise. Which swing will go for a very long time? Oscillate for a long time. No noise. What happens? Here there is a lot of, yes, friction, lot of friction. Okay, so because of friction, there's a loss in energy. It's a big loss in energy. Agreed? So this means when you are having free oscillation, something could be there to slow down or stop your oscillation. In real life, the oscillation doesn't seem to go infinitely. It may go for a long time, but then it doesn't go infinitely. Right? You agree on this point? Okay. Because I'm going to ask you what you understood at the end of the class. So please do pay attention. If you are having doubts, ask. Please ask. So next type of vibration is the forced vibration. So you got a free vibration where the body is allowed to move on its own accord. Nothing is asking it to move or nothing is preventing its motion. The initial motion was started and then we are just sitting back, watching the fun. What is the swing doing? Okay, or what is this bell going to do? Okay, so here what happens, in every case there is some kind of mechanism where energy is getting lost. Because energy is getting lost, vibration stops. Vibration is not happening because of the loss in energy, not because of anything else. Not because of anything else. Okay. The next kind of vibration is the forced vibration. So here what happens, there's something which causes the excitation and ensures that the excitation keeps on happening. For example, suppose you take a centrifugal pump, you see the motors, there's a motor, there's a pump. So the pump keeps rotating continuously, it's keeping on giving some energy, it's causing it's forcing the vibration. Okay, again look at the cell phone. The cell phone vibrator motor is going to turn for the vibration to be continuous. So the vibration will continue till we are having that excitation. Okay, so this is what we call as a forced vibration. Okay, now if you are given a situation where there is an earthquake, is it a free vibration or is it a forced vibration? Why? Okay. Don't worry, tell. Visualize it. Okay, I'll give you one more example of a forced vibration. In your school, did you have that calling bell? Yes, that big bell and yeah. So now, there if you look at it, to hear the sound, you keep pressing the button. Okay, when you remove the finger, the vibration stops. Okay, the vibration of the gong stops and it continues till it's having energy. This is an example of forced vibration. Typically, if you look at the earthquake and other things, there is an initial vibration. After that initial vibration, nothing happens. The excitation is stopped. The structure starts to react. Okay, but maybe suppose you look at a earthquake which is having a rather which is happening for some time, for a duration. If the structure fails before the base excitation stops, that means it is a forced vibration. Okay. Now the reason why I asked you this question is that the answer what you told was right, but in the explanation is what we are looking at here. For example, if you look at there was a photograph of some of the structure, I mean after the Hiroshima Nagasaki blasts. Now with the amount of energy which was released during that atom bomb, you probably think all the structures would have collapsed. But then what happened is the tall chimneys were not affected. They looked the same. So that looks like a little funny sort of stuff. See, the bomb exploding, there could have been so many reasons. Okay, the one shock wave would have decimated the buildings. So many things could have happened. But here what happened is the structure managed to have a response or respond to the excitation. It can be a blast load, it can be a base excitation, it can be any of the other kinds which happen. But what is the main thing we are looking at? The tall chimneys manage to be safe. Okay, so it means that there is one part, okay, where the structure is able to stand even after the excitation stops. So when we are looking at if the structure fails when the excitation is happening, that's a forced vibration sort of failure which you can put it. But then what if the structure stands even after the shock? It's a very short period when the shock is happening. It's set to vibration. So at that time it freely vibrates and then it comes to rest. So basically you need to just look at free vibration as where the structure continues to have the response even after the forcing frequency has stopped the excitation. Forced vibration means the vibration keeps continuing even after the what I'll say is the vibration is happening as the forcing function or forcing system is still there. See, there are a lot of places where forcing function takes place. very common examples are vehicles on a bridge. Okay. Now the vehicle on a bridge can give a excitation, go away from the bridge pier which is under question. You will still find that sometimes the bridge pier vibrates. So when the vehicle has crossed it, then it is having a free vibration. But when the vehicle is on the bridge, there can be small cracks or something which make the vehicle go up and down. So there, like a random sort of excitation is there. There is a forcing function and there is a forced vibration. Okay. So maybe when we are looking at civil engineering, this bridge will be a very common example. Another very common thing which happens is where you are going to have some machinery on a building. Okay. See, for example, there is an air conditioner unit. The air conditioning unit has a motor, and many of the times you will hear the AC making a lot of noise, outdoor unit making a lot of noise. Something is not in alignment, so if you touch it, it's vibrating. The same thing, you just extend to your system. So the system can be vibrating because the agent causing the change is vibrating. In that case, it would be the air conditioner outdoor unit. It will be the air conditioner outdoor unit. So you will be you will, when you are looking at things like this, there are so many what I call as ifs. If this thing is vibrating, something happens. If this thing happens, this happens. So like this. So it means that maybe this fan is also vibrating. It's causing a excitation. So this is a forcing function. And I worked in bulk material handling. So we used to have conveyor galleries. The motors cause vibration on the structure. We had crushers. Crushers will cause vibration on the structure. So vibration in some cases are good, in some cases it is bad. All vibration you cannot say is bad. All vibrations are not good. But vibration causes fatigue. Vibration can cause a structure to start to oscillate and have displacements which are not good, which are not going to make you comfortable. The oscillation, okay, vibration is used for consolidation of soil. I don't know, you have seen that vibro compactors. When they start the vibration, the whole feet starts to tickle, right? And did you see how the road looks after that goes? It's like taking an iron box and steam ironing the road. The road looks so nice once the vibro compactor goes. But the same vibro compactor, when it is vibrating near another building, it can cause a lot of settlement of soil, and that can be detrimental to the building. Okay, so we cannot say closing our eyes vibration is good or vibration is bad. Okay, so by now I hope you understand what free vibration is and what forced vibration is. Okay, right. Now if you look at this, this is taken from Wikipedia. This is free vibration. I'm sure you are able to understand, like from the mean position there's a displacement and it keeps on oscillating about its mean point. Keeps on happening. There is no damping. Because there is no damping, you will actually see that let me just turn on my pen. Yeah, you will actually see that the peaks are constant. Peaks are constant. This is a case of free vibration where there is no way by which energy can get lost. But it's very difficult in twisting the spring and untwisting the spring itself. Energy will get lost in the form. This will be dissipated in the form of heat. But suppose you are putting it in vacuum, you got no air to disturb it. So that time it will go for a much longer period. But that's about it. Next, there is something called the underdamped system, where energy loss is there, but it kind of comes to rest over a long period of time. Comes to rest after a significant period of time. See, initially the displacement is zero, but then there is a lot of acceleration which you give. Okay, so then you will see that the acceleration or no, there is no acceleration when it comes to rest. And this system over here gives you the displacement. Okay. Any questions on this? See, the previous case, we assume a very idealistic situation where nothing is there to make the system lose energy. Nothing is there to make the system lose energy. It's like taking a car or a bike and saying that I am giving a large acceleration. When I release it, there's nothing to stop you. So I keep going. Okay. See, for example, if you look at the electric trains, as long as you hear that sound of the motor, that's the only time when it's powered. When the motorman turns off the power, it just coasts, it just keeps going. On a steel to steel, there's very less friction. There's no lot of bumps like on the road, so the train can just keep going for a very long time. This is like that example. So where nothing is there to significantly make it lose energy. So the oscillation is going to continue for a very, very long time. So here we say damping is 0, or the way by which energy is going to get lost is 0. Clear? On the other hand, in this case, it's a more realistic thing, like the swing. Initially, the swing would have been in 0. You give a initial displacement and then it starts to accelerate, change its velocity, so on and so forth. So you got a curve over here. So the system doesn't vibrate as to the extremity as it did in the initial stage. It slowly comes to a much lesser or smaller level till the vibration ceases altogether, right? So this is a damped system basically, okay, where there is a way by which energy gets lost. Under damped system, it means the damping is such that the system doesn't come to rest very fast. Maybe we should have looked at critically damped initially. See, the system comes to rest and it just stays there. It's not taking the energy back. Okay, so if you look at it, the displacement is there, but after that it stays at rest. Okay, so from the mean position you had displaced it. Okay, and when you released it, it started to come, but then it doesn't go back at all. Okay, now this means it is critically damped. But the definition of critically damped is the damping, amount of damping which you have to give to the system so that it comes to rest the fastest. Okay, so when we call critically damped, when we say that a system is critically damped, that system will come to rest very quickly, much more quickly than any other case. Okay. Now look at this. This is a over damped system. So here what happens? It comes to rest, but not as fast as the previous case. Okay. So here almost in 2 seconds of time, like it's come to rest. But here it comes to rest. It comes to rest, but after a little longer time. So whenever a system is over damped, it's not again going to show vibration or oscillation. Okay, but the time it takes to come to rest is much higher than a critically damped system. Okay. Now I do have a few videos, but I don't know whether they will work, because typically if they don't work on one computer, if they don't work, they just don't work, right? It's not working. So what I'll do is I'll stop now. We will continue with these videos in the next class. Okay. So what I'm doing is I'm just going straight. I'm going to say thank you to you. Okay. So we'll meet again tomorrow. We'll meet at 4 o'clock. We do not yet fix the venue, so we'll do that right now. Okay.